Hi, my name is Jerry Peng, and this presentation looks at how we search text that's stored in databases, and how we can implement a semantic search rather than just relying on keyword matching. To understand the problem, it helps to first look at how text is usually searched in relational databases. In a typical SQL database, searching text is done using exact keyword matching. This means that the database looks for entries where the query word appears in the text. If the word isn't there, the row simply won't be returned. This works well for structured data like numbers or categories, but it becomes very fragile when dealing with natural language. Two sentences can be very similar in meaning while sharing few or no exact words, and in those cases, keyword search won't be able to find any similarity. So even though the information we want might be present in the database, the system has no real way of recognizing that it's relevant unless the wording matches exactly. The main issue with keyword-based search is that it treats text as just a sequence of characters, rather than something that carries meaning. For example, if someone searches for the word love among these movies and their plots, only the movies containing the word love will be returned, even though all of these movies are categorized as romance and could certainly match that word. Small changes in wording, pluralization, or phrasing can cause relevant results to be missed entirely. So the problem is not that the data isn't there, but that the database has no understanding of semantic similarity. It can only match text, but not meaning. And this problem matters because text data shows up everywhere, and a lot of it still lives inside relational databases. Things like product descriptions, movie plots, articles, and documentation are often stored as plain text fields, but the tools we use to search them don't reflect how flexible language can be. In many cases, users don't know the exact wording used in what they're searching for, they just know the general idea. This makes it nearly impossible for them to find what they want. So the motivation for this project is to see how we can make text search more flexible and meaning aware. This is something that could strongly improve database usability and make tasks much more efficient. Given the limitations with the current method of search, the objective is to change how text is compared during search. Instead of just treating words as plain strings, the goal is to represent word meaning in a way that allows for similar ideas to be recognized, even when the phrasing is different. This makes using letters very difficult, since you can't really tell if two words are similar or not without already knowing the definition of each word. With a more flexible representation in place, search can be done by comparing meaning rather than just checking for keyword matches. This would then allow for conceptually similar results to be retrieved, even in cases where the query words don't appear directly in the text. Also, a key part of this objective is to make this work within an SQL database, so that the semantic search can be used on top of existing systems, rather than requiring a completely new infrastructure. To compare meaning rather than exact text, we can represent words numerically by using word embeddings. With word embeddings, each word is represented by a vector, essentially just a list of numbers, which capture what word is used in the language and how. It may seem strange that numbers can hold semantic meaning, but we're soon going to see exactly how powerful they are. These vectors are learned from large collections of text by looking at the contexts in which the words appear. An important property of these vectors is that words with similar meanings tend to have similar vectors, specifically on a component by component basis. That means we can compare words by comparing their vectors instead. This gives us a way to measure actual similarity between words, which is something keyword search can't do. One interesting property of word embeddings is that they don't just allow us to compare words, they also support arithmetic operations. Because words are represented as vectors, we can add and subtract them to explore relationships between them. A classic example of this is taking the vector for the word king, subtracting man, and adding woman, which results in a vector that is very close to the representation for queen. This is not a coincidence. This works because the embedding space captures the underlying relationships, such as title or role, in a very consistent way. For this project, I worked with two different sets of word embeddings. The first is a set of embeddings called the Global Vectors for Word Representation, or GLOVE. These embeddings were trained using unsupervised learning on a very large and diverse dataset of text, which makes them very general purpose and effective across a wide range of topics. Because of the scale of the training data, they're able to capture much more broad semantic relationships, but they also require a long and expensive training process. The second type of embeddings were custom trained as part of this project. These were trained on a dataset of tweets from alleged Russian Twitter bot accounts during the 2016 American election. This dataset is much smaller and much more domain specific, which makes the embeddings more niche. The benefit is that they can be trained much more quickly, but the trade-off is that their semantic understanding is limited to mainly the content that the data was actually trained on. On the right are some of the hyperparameters that were used in the training. Comparing these two embeddings allow us to see how training data size and domain will influence semantic quality and the usefulness of the embeddings. To create the custom embeddings from the Russian tweet dataset, the first step was to cleanse the data. This involved removing things like URLs, user mentions, and other elements that don't really contribute useful information. The goal was to keep only text that shows how the words are used in context. After pre-processing, I used the word-to-vec algorithm to train the word embeddings on the clean dataset, which runs the data through a neural network. This produced vector representations that reflect patterns and relationships specific to the language used in those tweets. This slide shows a direct comparison between the pre-trained GLOVE embeddings and our own custom embeddings trained on the Russian tweet dataset. For each model, I looked at the 5 most similar words to Putin, Russia, and king. The table on the left shows the results from the GLOVE embeddings, while the table on the right shows the results from our custom trained embeddings. In the GLOVE model, the nearest words are consistently meaningful across all 3 queries. For example, Putin and Russia returned related geopolitical terms, and king returns words like prince, queen, and monarch, which are words that we would expect to be most similar. In the custom trained embeddings, the results for Putin and Russia are also relevant, which makes sense given how frequently those terms would appear in the Russian tweet dataset. However, the nearest words for king are much less relevant, suggesting that this word did not appear often enough in the training data for the model to learn a really reliable semantic meaning for it. What this comparison also shows is that the embedding models don't fail randomly. They fail in a very predictable way. Words that are common in the training corpus tend to be represented clearly, while words that fall outside that core domain are either poorly represented or just missing. This makes it important to think carefully about how and where embeddings are used, especially when they're trained on specialized text. In practice, this means that embeddings are most reliable when applied to text that closely resembles the data they were trained on. And this just highlights how strongly embedding quality depends on the size and domain of the training data that was used. After looking at how word embeddings behave on individual words, the next step was to see how well they could be used in a more practical setting. Specifically, to test whether embeddings could help categorize and retrieve movies based on their overall themes. To do this, we created a small dataset of 30 movies evenly split across the genres sci-fi, action, crime/thriller, and romance/drama. These genres were chosen because they are conceptually distinct but share some overlap in language. Each movie was then represented as a single vector by combining the embeddings of all the words in its title and plot description. This was simply done by averaging the vectors for each word, which produced a compact representation that captures the overall meaning of a movie's title and plot, all in one vector. The image here shows just how simple the averaging the vectors really is, since it only involves adding up the corresponding components from each vector and dividing by the amount of vectors present. Once each movie was represented as a single vector, the next step was integrating those representations into a database. Each movie was stored in a relational database with its plot description, and the computed vector representation. Because the movie vectors are created by averaging word embeddings, they live in the same space as individual word embeddings, meaning they have the same amount of dimensions. We couldn't compare two vectors if they had a different amount of dimensions, since there would be missing components, meaning they couldn't be averaged properly. This is important because it allows us to directly compare a query word with an entire movie description, which is something we could not do without using these embeddings. With both words and movies now represented with comparable vectors, we can perform a semantic search. For a given query word, the system retrieves its vector representation and compares it to each movie's vector. To measure how closely these vectors are to one another, cosine similarity is used, which looks at how aligned two vectors are. Each movie is then ranked based on its similarity score to the query word, and the highest ranked movies are the ones returned as the most relevant results. This allows the system to retrieve movies based on conceptual similarity rather than just keyword matching. Here is the list of movies that were used. As you can see, there were 3 categories with 10 movies in each. Each of the movies clearly falls within its respective category, which makes classification more straightforward. Although there can be some movies from different categories that are similar to one another, for the most part they are pretty well separated. Here are the query results for the word love. You'd probably expect that the word love is most similar to movies from the romance and drama category, and that's exactly what happens. As you can see here, the top 5 most related movies are Pride and Prejudice, La La Land, Me Before You, Crazy Rich Asians, and A Star is Born. These are all from the romance and drama category, which makes sense for this query word. The cosine similarity score was also included, showing exactly how similar each of these movie vectors are to the vector for the word love. Then, when querying for the word crime, the 5 most similar movies are Seven, Goodfellas, Scarface, Pulp Fiction, and The Departed, which all come from the crime and thriller category. And for the word space, the most similar movies are Interstellar, The Martian, Avatar, The Matrix, and Titanic, which are mostly all science fiction and action films as expected. The only surprise here would be number 5 Titanic, which falls into the romance category. So these vectors representing movies aren't perfect in their understanding, but for the most part they do a fairly good job of condensing the information in each title and plot and being able to create meaning out of it. One thing that's very interesting about the embeddings is that it's difficult to know exactly why a word received the vector embedding that it did. Embeddings can be trained in many different ways that lead to different results, many of which involve using neural networks or different types of learning. The results show a clear pattern when using semantic search. Words that are strongly associated with a particular genre tend to retrieve movies from that category very consistently. What's even more interesting is that this still works even when there are no keywords that overlap. For example, when we queried the word space, the movie Interstellar was ranked as the most relevant result. despite the fact that the word space does not explicitly appear in its title or plot. This highlights the key advantage of semantic search, which is that relevance is determined by overall meaning, rather than exact word matches. These results show how embedding-based representations capture high-level theme information that keyword-based search methods are not able to detect. Another important aspect of these results demonstrate is that the semantic search behaves more like a ranking system than a strict filter. Rather than deciding whether a movie is relevant or not, the system assigns a degree of relevance, such as cosine similarity, based on how closely the overall meaning aligns with the query. This means results don't have to be perfect for them to still be useful. Instead, they provide a ranked list that surfaces the most conceptually related items first. In practice, this is oftentimes more helpful than keyword matching, which would either return an item or just ignore it completely. These results also suggest that the same approach could be used in the opposite direction, to identify items that are least related to a given query. Because similarity is measured on a continuous scale, it becomes possible not only to surface the most relevant results, but also find movies whose themes are conceptually far away from the query word. This opens the door to some alternative ways of exploring a dataset, such as deliberately seeking contrasting content or understanding how different themes are separated in the semantic space. While this was not the focus of the project, it highlights the flexibility of embedding representations beyond just a simple search. To summarize the main findings of the project, there are a few key ideas that consistently showed up. Firstly, the results clearly show that words with similar meanings can be represented by vectors that are close to one another in an embedding space. This makes it possible to compare words based on meaning rather than just exact spelling, which is fundamentally a big shift from how typical text search works. Instead of asking if two words match exactly, we can ask how similar they are semantically, which aligns much more closely with how people actually think about language. Second, this project highlights just how strongly word embeddings are shaped by the data they are trained on. Embeddings trained on large, diverse corpora, for example, like the pre-trained Glove embeddings we saw earlier, tend to capture broad relationships and generalize pretty well across many different topics. On the other hand, embeddings trained on smaller or more specialized datasets reflect the biases and limitations of that data. In the case of the custom embeddings trained on the Russian bot tweets, the model develops strong representations for frequently occurring geopolitical terms, but at the same time, it struggled to represent words that fell outside of that content, like king. This reinforces the idea that embeddings are not inherently neutral or universal. They're a direct reflection of their training data. Another important finding is that the meaning of a sentence can be compressed into a single vector using relatively simple techniques, such as averaging word embeddings. While this approach ignores things like word order, syntax, and some of the linguistic structure, it still does preserve enough high-level semantic information to identify the overall meaning and themes. In the context of this project, averaging embeddings was sufficient to represent movie plots well enough, but can definitely be expanded on for future exploration. Taken together, these findings show that even simple embedding-based methods can provide real value when applied. Even without relying on complex models or specialized infrastructure, it is possible to enhance relational databases with meaning-aware search capabilities. At the same time, the results make it clear that the effectiveness of these methods depends heavily on the data quality, domain relevance, and representation choices. Understanding how these trade-offs work is important when deciding how and where embedding techniques should be applied. Thank you so much for watching. I hope you enjoyed the presentation.